As a chemical engineer or a scientist, it is your job, after knowing chemistry, to not only know how to make materials, but also know how fast those materials are made. So, uh, that branch of science wherein we deal with how fast and how slow a reaction goes, that's called chemical chemical kinetics. Chemical kinetics. And the goal of this video would be to introduce chemical kinetics and specifically introduce the rate of reaction that's going to be our tool throughout chemical kinetics and throughout chemistry as well. So basically in chemical kinetics we're talking about how fast a reaction goes. Thermodynamics talks about whether a reaction is spontaneous or not, whether it will happen or not. However, chemical kinetics talks about how fast a reaction will happen. So, for instance, let's take one of the most common examples taken throughout chemical kinetics, the reason being there has been so much research about it, and it is the decomposition of dinitrogen pentoxide. Now, if you look at nitrogen pentoxide, and what you do is on one axis you take the time in whatever units you want. Let's take minutes or seconds, whatever you want. And here, what you do is you take the concentration in molars. So molar is just mole per liter. And once you do that, what you're basically plotting is, as time progresses, as time moves forward, how much of each compound is being formed, how much of nitrogen dioxide is being formed, how much of oxygen gas is being formed, and how much of nitrogen pentoxide is getting used. Now, let's take a moment to analyze this graph. So, nitrogen dioxide, it's in the product side, so its concentration is increasing. Makes sense. Oxygen is on the product side as well, so its concentration is also increasing. If you look at the graph, it increases, and then after, let's say, some time, the reaction basically is left with no material, so the reaction almost goes to a point where the concentrations become equal, become constant. But then there is the reactant, the original reactant, dinitrogen pentoxide. And since it is getting used up, it's getting used up in this reaction, its concentration is decreasing. So this is decreasing, this is increasing, and this is increasing. Makes sense. Now what I do is I introduce a term, rate. Now what rate means is the change in the concentration over time. You can just remember it like that: change in concentration over change in time. Now what you can regard this as, so let's suppose that in time t, in time t in time t we used delta N2O5 is equal to the change in the concentration of delta N2O5, the concentration of N2O5 is equal to, let's say, negative 0.5 moles per liter. So what that means is that in some time t, where t is 1 second, 2 second, we don't specify that, in that time t, there has been a decrease in the concentration of N2O5. And when that happens, the concentration of the products must increase by a similar amount. So, well, you can use stoichiometry here. You can use basic stoichiometry. So, N2O5 gives 2NO2 plus half of O2. Now, if you use X moles of N2O5, you should produce, using X moles, we are taking in moles or molars, you will produce 2x moles of NO2, 2x moles of NO2, and half x by 2 moles of oxygen gas. That's basic stoichiometry. So that means that the change, since you have this stoichiometric equation, you have that the change in the concentration of NO2 is double the change in the concentration of N2O5. So you could have written 2 times 0.5 moles per liter. Now, why didn't I write the negative sign? Because NO2 is increasing, the concentration of NO2 is increasing. And similarly, I could write that the concentration of O2 increases by half times 0.5 moles per liter. Once you have this, notice that you also need to take care that the rate should be equal for the entire reaction. So that means is if you just wrote, this is by the way, this is a chart of the different values that you will have, but let's focus on the discussion that we are having. So if you divided all of these by delta T, so delta N2O5 over delta T is equal to delta NO2 over delta T is equal to delta O2 over delta T. Now, what am I missing in this equation? All of these are equivalents of writing the rate. What am I missing? I'm missing a few things. First, N2O5 dinitrogen pentoxide is decreasing, so the rate must have a negative sign with it. The rate, remember that the rate is always positive, always positive, and you have to do anything to make it positive. So with reactants, you put a negative sign. So this thing is sorted out. Let's move on to the expression for NO2. Now if you see, if you divide this expression both sides by 2, then these two equations are actually equal. These two equations are actually equal. So because 1 mole of N2O5 produces 2 moles of NO2, the rate of formation of NO2 should be one half of the rate of decomposition of N2O5. And similarly, if you take O2 for example, so 1 mole of N2O5 decomposes to give half moles of O2. So that means that the rate of formation of O2 should be double the rate of, should be half times the rate of decomposition of N2O5. So in this case, you will put a 2 here. So in order to generalize this, you can do, if there is a reaction AA plus BB forming CC plus DD, in this case, what you'll do, firstly, let's write it for the right-hand side, for the left-hand side. So firstly, you put a negative for all the reactants that you have, and you divide it by delta T. And then you write the similar thing for B. B is also a reactant, so you put a negative sign there as well. C is a product, so you don't have to put a negative sign there. It's always increasing. And D is also a product, so you just write it in like that. And now you write in the coefficients. You write in these coefficients. And what you do is you just basically write them up like as so. For A, you write its coefficient in the denominator. For B, you do the same. For C, you do the same. And for D, you do the same. And that's it. That is sort of what we call as the rate law. The rate law of an expression. And what we can do now, we can try actually computing the rate. And remember, all of these expressions right here, whether it be this quantity or this quantity or this quantity, all three are equal, and all three are equal to the rate of the reaction. They are equal to the rate of the reaction. So let's try estimating the rate of the reaction. So I have here the values. So values of N2O5, NO2, and O2. So what I can do is I can write rate, whatever the rate will be, is equal to delta negative delta of N2O5 concentration divided by delta T is equal to half times delta NO2 over delta T, and is equal to 2 times delta O2 over delta T. And notice that you can just derive that also by using the equation that we had originally. So N2O5 forming 2NO2 plus O2. So that 2 comes here, and if you put in a half in the denominator, it becomes 2 in the numerator. Okay, now you could have used any of these three to actually calculate the expression. Let's just use this one. Let's just use the first part. It will save us some troubles. So the average rate of the reaction between 0 and 100 seconds, that is equal to, now you again put the negative sign, here, then the change in concentration of N2O5. So you're talking about 100 seconds minus 0 seconds. And the change in the concentration here would be at 100 seconds, the concentration of N2O5 is 0.0169. And at 0 seconds, the concentration was 0.0200. And notice you're not doing this for good math, so it doesn't necessarily require to have the bigger number first and the smaller number later, since the negative sign will just level everything out. So in case you're getting troubled by the sign, you can just remove that and always try to get a positive expression for the rate. And if you compute that, let's just compute that. So this will be equal to negative of the expression inside the brackets will be equivalent to writing negative of 0.031, and you're dividing that by 100 seconds. And this everything here is in molars, it's in molars here. So we also need to mention that. So 0.0196 molar and 0.0200 molars. And so molars are here, and then you divide them. So negative and negative would cancel out, and you would have this thing here. This can be written as 3.1 into 10 to the power negative 3, and you're dividing that by 100 seconds, so molars per second. And so this would be equivalent to writing 3.1 into 10 to the power negative 5 molars per second, or for molars, if you want to write moles per liter, then moles per liter second, or you could have written moles liters inverse seconds inverse. So that's how you calculate the average rate. You could have chosen any expression here. You could have chosen this one, you could have chosen this one, and for the interval between 0 and 100, you would have always got the same rate. And that's a brief introduction to chemical kinetics, and mainly we had an introduction to the average rate of change. In the next few videos, we will start talking about the instantaneous rate of change, and I'll see you in the next video.